Alright guys, so in this video we're going to talk about finding inverses for functions defined by equations. And in general right here we've got a procedure for finding the inverse equation for a given function. If we are in function notation, the first thing we're going to do is change f of x to y. So we're going to go from function notation to equation notation, which is going to give us y equals x cubed plus 2. And then the thing that we do to create the inverse is switch the x and the y. So right here, we switch the x and the y, and that gives us x equals y cubed plus 2. Now technically, at this point, we have an inverse. But in general, we want our inverses to be functions of x. And so that's going to mean solving for y here. So right here, the first thing we'll do in our solving for y is subtract 2 from both sides. And that's going to give us x minus 2 equals y cubed. And then to undo the cube, we're going to take the cube root of both sides. And that's going to give us y equals the cube root of x minus 2. So pretty easy. We've got our equation that defines our inverse of f. And so we would write it as f to the negative 1 of x, or f inverse of x. And that's going to be our cube root of x minus 2. Now, what we want to take note of right here is what we did to get this inverse equation, right? Or to get the equation of this inverse function. So right here, when we switched the x and the y, we said that at that point we had inverses, right? And when we solved for y, essentially what we did was undo what x was doing to the input, operation by operation. So the first thing we did was we subtracted 2 from both sides, right? And that, of course, undid the addition of 2, right? And then the next thing we did was we took the cubed root, which undid the cube. So essentially, the way we've constructed f inverse, it undoes what f does to the input, right? Similarly, we can see that if we look at the inverse's relationship to the function, right, f is going to undo what f inverse does to its input. So right here, if we look at f inverse, right, we would plug in an x, subtract 2, and then take the cubed root. If we plug whatever we just got out of f inverse into f, the first thing we're going to do is take the cubed root, which is going, or apply the cube, which is going to undo the cubed root, right? And then the next thing we're going to do is add 2, which undoes the subtraction of 2. So f actually undoes f inverse as well. And this relationship is the relationship that defines inverse functions, right? We're calling f inverse the inverse of f, but really they share an inverse relationship where they undo each other. Right here, if we're looking at the definition, we can prove that we have inverse functions by plugging one into the other and showing all the operations cancel. So if we plug the inverse into the function, all the operations should cancel, and we should just get x. And if we plug in the function to its inverse, all the operations should cancel, and we should just get x. So I'm going to do this one right here, and then I'll have you guys do this one right here. Should be pretty quick work. So right here, first we're going to take f of x, which is, of course, going to cube its input and then add 2. And we're going to plug in f inverse. And f inverse is going to basically be that cube root of x minus 2. Now the first thing we see is the cube and the cube root cancel out. And that is going to give us x minus 2 plus 2. And of course, we see that plus 2 and minus 2 cancel out, and we're going to get just x. So right here, we've shown it in one direction, and now we want to show it in the other direction. So your job is to go ahead and show that when we plug in f of x into f inverse, I'm going to do this in red so it looks neat, that we will in fact get just x as the output. So I'm going to pause the video now and let you guys give this one a shot. Okay, so looking at this guy, we've got f inverse of f of x. So f inverse takes its input, subtracts 2 from it, and takes the cubed root. And when we plug in f of x, that's going to be the equation that is x cubed plus 2. The first thing we're seeing when we take down those parentheses is that the addition and subtraction of 2 will, of course, cancel. And then we are left with the cubed root of x cubed, and of course the cube and the cubed root will cancel. and we are going to get just x. Right? So works in both directions. We've proven our inverse relation. Okay, so what we're going to do next is something a little bit different. We're going to find inverses, but what we want to do is go ahead and find the inverse equation, or find the equation of the inverse of the given function, then give the domain and range of the inverse. Now remember that the inverse is going to switch the domain and the range. And that happens regardless of what equation we end up with. So right here, if I have f of x equals the square root of x minus 3, then right here, finding my inverse, I would have y equals, and then right here, square root of x minus 3, and then this would be x equals the square root of y minus 3, and now right here, I solve for y, so I square both sides, and that's going to give me x squared equals y minus 3, and then I add 3 to both sides, and that's going to give me y equals x squared plus 3. And that is going to be the inverse of my function, square root of x minus 3. So x squared plus 3. So right here, what we want to take note of, though, is that if we just graph this equation, we would have the parabola moved up 3, right? And what we want to ask is all of the ordered pairs that make up this parabola, are those really the ordered pairs of our f of x inverse? Or the ordered pairs of our f of x inverted? Now, if we look at the graph of the square root of x minus 3, what we would see is 1/2 of a sideways parabola starting at the x value of 3 and sort of arcing out like that. So actually right here, because we only have the top half of the parabola, the entire graph isn't going to be the inverse, right? So I'm going to erase the math we did to get the inverse and show you guys where we're going to get the domain and the range for our inverse. So right here, looking at our f, we could say that the domain would be from 3 to positive infinity. And if we looked at the graph, we would be able to see that the range would be from and including 0 to positive infinity. And that means that for the inverse, we are going to have a domain of, right here, 0 to positive infinity and a range of 3 to positive infinity. And that is going to give us an inverse graph. So right here, we've got the graph of our f of x as that half of the sideways parabola. And if we define our graph of f inverse on this domain from 0 to positive infinity, we're just going to get the ordered pairs from that sideways parabola reflected across the line y equals x. And that would define the inverse. So right here, this is really a special case. It's not going to happen for all of them. What I would say is before you go through each of these, what you want to do is determine the domain and the range. And then just at the end, when you've found the inverse, you're going to switch the domain and the range to give the domain and range of the inverse. All right, so what I want you guys to do now is to give B and C a shot. If you want to give D a shot, you can. It's a little tricky. If you do give D a shot, we'll look at it tomorrow in class. And in general, what we'll say is that right here, before you switch the x and the y, what you want to do is write this guy in vertex form. So you've got a series of things happening to one x. But when you switch the x and the y, you're going to be able to undo to y. And you're going to end up with two equations defining the inverse here. And that should make sense to us because this is the parabola that looks a little something like this, right? So its inverse is not going to be a function, but we can define that inverse with a pair of implicit equations. We'll talk about that tomorrow. But right now, what I want you to do is pause the video and give B and C a shot on your own, and we'll come back and look at those in a second. All right, guys, so with B, when we look at this function, g of x, we are seeing a domain that goes from negative infinity to negative 5, union a negative 5 to positive infinity. And if we look at the graph of our g of x, basically what we're seeing is a function that is responding to a vertical asymptote and a horizontal asymptote at 0, which is keeping it from attaining the y value of 0. So the range right here is going to be from negative infinity to 0, union with 0 to positive infinity. So right here I combine two steps. I change g of x to y, and I switch my x and my y, so I've got x equals 5 over y plus 5. Right here we're solving for y, so I multiply y plus 5 on both sides. That's going to give me xy plus 5x equals 5. Then I isolate the y term by subtracting 5 on both sides and divide by x on both sides, and I get y equals 5 minus 5x over x as my inverse. And of course, for this inverse, we are going to, I'm going to bring both these down so we can see it a little better. We are going to have a domain, which is the range of the original function, and a range, which is the domain of the original function. Now, this is the relationship between most functions and their inverses. And it's actually a way that we can solve for the range of an original function without looking at the graph. Right here, if I invert g, right, I can say that the domain of g is going to be the range of the original function, right? So I can algebraically solve for the range in that way. So looking at C, right here we have the graph of k of x as 5 minus the square root of x, and that's going to be a graph that is basically the square root of x made negative, so flipped upside down, so that's 1/2 of the sideways parabola upside down, and then we've got 5 added to it, which moves it up 5, which gives us a graph that looks something like this. The domain we can get pretty easily as going from 0 to positive infinity. The range, on the other hand, is going to start at 5 and then go down to negative infinity. Right here, when we want to go ahead and find the inverse here, again, I changed my k of x to y and switched x and y, so I've got x equals 5 minus the square root of y. And when I'm isolating y, the first thing I'm going to do is subtract 5 from both sides. Then I've got a negative square root of y, so I multiply negative 1 on both sides, and that's going to give me 5 minus x equals the square root of y. And then I square both sides to get rid of the square root, and that's going to give me my inverse as the square of x minus, or 5 minus x rather, and that is 25 minus 10x plus x squared, which we can also write as x squared minus 10x plus 25. And this is going to be on the domain that is the range of the original function. So right here, we're basically saying we're going to have this graph, but only on the domain that goes from negative infinity to 5. And basically what we're seeing here, if it goes from negative infinity to 5, I'm going to try to draw this in a way that looks like a reflection, is a graph that looks like this, extending out negatively. And this is a bad drawing, but basically if we sort of thought about this line as being y equals x, we would see that reflection across the line y equals x between our function and its inverse. All right, so these two problems are the ones that we are looking at now. We'll look at D tomorrow if you guys want to give it a shot, and we will do a worksheet in our class on Thursday. All right, here we go. Stop the video now.